Okay, great. So I'm really happy that we've got Konstantin Flemmer here from Microsoft Research. He's a postdoc at Microsoft Research New England, actually visiting London, so managed to make a trip out here. Part of the machine learning and statistics group, and his research focuses on representation of geographic phenomena in machine learning and machine learning methods in neural networks. And his recent work includes the integration of notions on spatial dependency into neural networks and unsupervised training of location encoders. And he's been motivated by work on climate change and urbanization. He has his PhD from the University of Warwick in computer science and urban science. And he spent some time at NYU, at the Turing Institute, and at TUM and DLR. So he's been around the world, and today he's here. So thank you very much for coming, and we look forward to your talk. So.
Thanks so much. Yeah, thanks for inviting me. I don't know if people see this annoying Zoom thing, or it will go away. But
I just want to say that battery's still not on, so
that's not
on the side, yeah.
That's fine. This we can solve it.
Sure.
Oh, these three wait until sorry, I have my magic turner on the Dumbledore one.
Oh, right.
I'll point it just right and go Illuminatus.
Yeah, we're good. Brilliant, thank you.
Okay. Yes, Zoom is still unhappy, so maybe you see that thing on the top. I don't know why that won't go away, but that's okay. I think most of you can see the slides. Yeah, thanks for having me. Yeah, cool coincidence. I was kind of planning to come here. Oh, hey, how's it going? Yeah, so it's been a while since I was in UK, but kind of overlapped nicely with coming here. And today I'm mostly talking about two papers, but kind of more general research which I have for the years to come. And that is one about geographic location encoders. And what I think those are, I'll elaborate on in my talk. But kind of motivating thing behind all of my research is this fact, and this is something that everyone who's worked on GIS probably has seen at some point. 80% of all data is geographic. It used to be part of even Esri's marketing materials. I think they've kind of removed that ever since. And if you want to learn more about this phrase, there's a great GIS Lounge, which is a blog post that kind of digs into this statement and tries to find an original attribution, because turns out that 80% of all data is geographic is kind of just based on urban legend in the GIS community. And it's not necessarily true. But I think what we can kind of say undeniably is that a lot of the world's data is geographic. And that goes from explicitly geographic data like satellite imagery to data where it's more hidden in the metadata. Like if you snap a picture with your cell phone, there's in theory at least, there's a geotag for that. Or if you send off a tweet or whatever it's called now, X, there's also a geotag that is being collected. And yeah, I think geographic data also is shown to be extremely useful in all sorts of real world scenarios. This here is probably also something that a lot of you are familiar with. My favorite map maybe, that is the famous Jon Snow cholera map. So when there was a cholera outbreak in London, Sir Jon Snow, who has a pub named after him, which is Life Goals, he managed to basically plot the different occasions of cholera, the different cases, map them out, and found that they were all clustering around a pump in Broad Street. And that way, basically figured out that cholera is being transmitted through water. And so pandemics is just one example, right? Climate change is another great example. And the industry that is kind of attached to analyzing geospatial data is massive. It's a $60 billion industry. It's a bit more like on the low side. It's not very like the most famous industry, but it serves as a kind of toolbox for a lot of bigger industries. And I think insurance is a great example. So on the right here, you have a flood insurance rate map. And that is basically a map that defines if you have a house in these areas, what kind of insurance premium are you going to pay for that? And basically what defines how insurance companies set those maps is very much based on geospatial analytics. And so the better you get, the more money these industries have. And the last bit of information is just kind of the data is out there kind of point. And we are at a point in time where there's so much geospatial data out there, and there's both on like planetary level, which is, for example, free satellite imagery that you can get from stuff like the planetary computer at Microsoft, but also data that is more constrained to a given area. For example, the London data stores a lot of kind of London-specific open data. And yeah, new products are launched continuously. We're shooting up so many satellites into space. There's kind of new missions coming that are providing free imagery, and then there's obviously also the missions from private companies like Max or Planet that provide imagery for money. Now, a lot of this data is unlabeled, of course, and requires kind of a lot of pre-processing and kind of fusing of different modalities together. And I think what really can be useful for analyzing all of that data is unsupervised learning. And this is really kind of the big overarching point I want to make, is that we can leverage unsupervised learning to help make sense of geospatial data. And specifically, this new paradigm of foundation models that came up big time in the last 2 years, maybe is one that I want to exploit here. And I say foundation models like LLMs because everyone knows LLMs, but there's other foundation models. And when I use that term, it's still a very ambiguous term and somewhat controversial. I basically mean it's kind of a large neural network model trained using some self-supervised learning objective on large amounts of data. And I want to kind of talk a little bit about 3 different foundation models types that are out there, and then I will kind of pitch what I believe could be a new type of foundation models in the geospace. So I'm going to first talk a little bit about LLMs, vision models, and also geophysical models. And let's start off with the geophysical models. So this is kind of a type of foundation model that basically tries to emulate physical processes of our planet. ClimaX, which is also from collaborators at Microsoft, is one example here. And basically, you can think about these as models that are leveraging deep learning to try and play some of these very expensive numerical emulators we have of physical processes, right? So a lot of different tech companies are trying to basically build climate models that are fast and flexible and can, in the long term, replace the very expensive numerical simulations we have. Next up, vision models, and this during a group discussion, of course. These kind of big foundational vision models can also be used off the shelf directly for geospatial data, like remote sensing data, and usually quite good at this off the shelf. And then, of course, you can get specialized foundation models. So this is a model that was launched at the World Economic Forum. It's called the Clay Foundation Model. Basically, a huge mass autoencoder trained specifically on remote sensing data. And the last thing I want to talk about is LLMs, because they do also have some intuition for geospatial data and for geographic concepts. And I want to show you kind of 2 very brief examples, and they're not meant to be exhaustive in any way. But like one example where they're actually quite impressive and one example where they fail pretty miserably. So one thing that LLMs can do pretty well is kind of provide information about a given location. And here, for example, I've just, sorry, the text might be a bit small on these screens, but basically I've dropped a pin somewhere in the middle of Texas and asked the GPT-4 to describe that location to me in all detail it has. And that includes natural, physical features, but also kind of socio-demographic factors. And the answer it returns to me is actually quite useful. It's pretty impressive that it kind of can deduce all of this from a location. Keep in mind, though, this is in Texas, so this is an area where we can assume that the model has probably seen quite a lot of training data. Now let's do a bit of a different task. And maybe also broadly, there's a whole research field that looks into this. It's called geographic question answering. It's a bit of a at the intersection of AI and GIS, basically. Now, one example where LLMs fail pretty miserably. So here I again drop a pin and I ask the model to predict, not to predict, but just to give me the annual mean temperature at this location. Now, the pin I drop is in the middle of the Pacific Ocean. So the model probably doesn't know what the annual mean temperature there is. But in my mind, at least, it should probably find the nearest location, has that information before, and then return that information along with the distance between the pin and where it has that information. And it's at least trying to do that, right? It says this location is about 1,000 miles east of the coast of Japan. And then it gives me the annual mean temperature for that location in Japan. Except that distance calculation is completely off. This location is more like 5,000 miles away from Japan, and a much nearer location that it does have data for would, for example, be Hawaii. And so a task that should be pretty easy kind of fails. And overall, I feel we can do much better. And I think actually that we can kind of combine these different geospatial modalities that we have. We can combine text, we can combine imagery, and then kind of geophysical data like climate data in one model together. And the way I think we should go about this is by using the joint geospatial information that all of these modalities have, and train geographic location encoders. And now I want to kind of first line out what a location encoder is, and then talk a bit about some specific research challenges in building them. Okay, so let's revisit the idea that geospatial data is in a shared geometric space, which is our planet. So we might have something like a satellite image. Here, this is San Francisco satellite image at a given location. Then we have something like a tweet that is sent from a specific location. And then we might have a complete different modality like a digital elevation model or an NDVI, whatever, at a different location. Now, the idea for geographic location encoders is that we train neural networks to match a given data input with the location it comes from. And the way to go about this is to feed your data through a multi-model encoder that can take any modality. You can think of this like something like a perceiver I/O. And then we take our metadata, our locations, feed that through a location encoder, and then we do some contrastive learning and try to match the location with the data modality. And if that training goes well, what we should get is a location encoder that learns a semantic representation, an implicit neural representation of any given place on the planet, and can return meaningful features for that location. And we can then downstream query these features and use them for kind of any task that would require some geographic information.
So why do you say contrastive learning? What is the purpose of that?
The idea here is that different data modalities, and let's maybe just stick for satellite imagery because we actually have a prototype for that. The idea here is that satellite imagery contains features that kind of uniquely identify a location. If you think about, let's say, a satellite image of a desert, that can only be in very specific locations on the planet. And so doing a contrastive learning task where you try to match an image to a location will force the model to learn exactly these features that make the image unique to a location. And when you then take your fully trained location encoder and query features from it, you may use these features downstream for kind of any prediction task that you would usually use satellite imagery for, except now you have it much more low dimensional and fast.
I can understand that for satellite images, that makes a lot of sense,
Yeah.
you know, because you're saying all these images are the same location, so find what's common to them.
Yeah.
But if you're doing tweets, then I don't see how that works.
Yeah, for a tweet, that might be much harder. If the tweet does not contain any location-specific information, it might be much harder. There is some intuition here that, for example, if the tweet is in English, it will come only from certain locations. If it's in a different language, it comes from other locations. And then there's this intuition that if you kind of stack different things together, it might give a better indication, right? So if you think about a stack of satellite images, some sentiment from tweets, and something else, this might be more uniquely identifiable than just a tweet. I would agree with that for sure.
And then when you say satellite image, how precise is that? Because the binning is going to make a big difference, right? Whether you choose a 10-meter resolution, 100 meter, 1 kilometer.
Yes, that makes a huge difference. In the paper that we finished, we use 10 meter, we use Sentinel-2. I will get to that in a bit,
Okay.
and then I can talk a bit about
Okay,
this.
sounds good. Thank you.
Great, thanks. Yeah, and so the two kind of things that I want to talk about in making or building like a first prototype of these models is first how to design good location encoders. how basically to embed latitude, longitude coordinates in neural networks. And then how do we actually find good training data to do this kind of contrastive pre-training of location and images. And I already spoiled that, it's going to be sentiment to imagery. Now, the ambitions that I see and the goals for location encoders, in the short term, it is making geographic features from higher dimensional data like satellite imagery available very cheaply, right? So the location embeddings that we train in our model are 265 characters long. Compare that to I don't know, 512 times 512 times 13 channel satellite image, which is huge. And there's a big demand, especially in low resource settings, for getting these kind of geographic features available at cheap. And yeah, linking here to a paper from one of my co-authors, Esther Rolf, who has kind of done some great work on this. And then the long-term ambition is really the big one, and that is that can we, using data, using Earth observation data, actually learn the physical processes that govern our planet and maybe our cities if we train such a model for a specific city, and it really goes towards building digital twins from data, ideally. Right, so let's get started with the first paper and talk about geographic location encoders. Just
It's big clock right there.
oh, perfect. Thanks. Right. So this talk is going to have very little math, but just very briefly, what do I mean when I talk about kind of the neural network component of a geographic location encoder? They usually take a form where you have lambda and phi, which are your latitude, longitude coordinates. Then you have a positional encoding PE. The positional encoding is a purely functional transform. There's no parameters to be learned here. And then on top of that positional encoding, you put a neural network that projects your coordinates into kind of any orbital space you might. And kind of originally motivated for this work was work by Ocean, who you might be familiar with at the University of Edinburgh, who has looked into the iNaturalist species classification data set, which is images of plant and animal species. And that is just a image classification task. And so he used the location of these images as kind of auxiliary information, encoded them, and showed that this actually gives you quite a valuable geographic prior and improves your predictions. And I've also done some work on this in the past, where I combined kind of positional encoders with graph neural networks, and also showed that this gives quite a neat improvement. And let me first start with saying how before this paper that we just published, location encodings in neural networks were done. And basically, the form that these location encodings have taken in the past is just sinusoidal transforms, basically Fourier transforms, all cases of what we call the double Fourier sphere, as we kind of outline in the new paper we just published. And I'll keep it very brief, but what that basically means is you take your latitude and longitudes and you sine, cosine them at different frequencies, stack that together, and that is your positional encoding. No parameters there, and then you put your neural network on top. Now, when we think about Earth modeling in geophysics and in the earth sciences, this is actually not the preferred way, which is really funny because it says that in the Wikipedia article about double Fourier sphere. And it says there that actually what geophysicists do much more is using spherical harmonics functions. And this is really what motivated this paper, is that we basically wanted to look if using spherical harmonics functions instead of these kind of Fourier-based functions, is this a better way of doing location encoding? Now, what are spherical harmonics? So spherical harmonics functions are orthogonal functions defined on a sphere, and they come out at different orders and degrees. These orders and degrees you can basically think of as equivalents to the kind of different frequencies we would use for stacking the sine cosines in the Fourier-based methods. And basically what that means is the more frequencies you have in the sine cosine functions for Fourier, or the more degrees you have for the spherical harmonics functions, the higher is the resolution of your positional encoding. If you only do one sine cosine, it's kind of a very kind of, yeah. Basically, if you only do one sine cosine for each lat long, you're basically gonna project your lat longs into like one big grid cell, transform it from the kind of spherical space to the rectangular space. And for spherical harmonics, kind of would be the same. Like the higher you go in your degrees, the more high resolution is your location plane. Now, I've put down the real form of the spherical harmonics down here. What is important to know is that you can do an analytical version of spherical harmonics, which is going to come in really handy when we actually use them in practice, because we can pre-compute them and don't need to kind of at every kind of forward pass compute new spherical harmonics. Now, the second thing we want to test out in this paper is kind of using a different neural network architecture. So on top of these purely functional position encodings, what people have used in the past is mostly fully connected neural nets, right? So these are just the layers you can see down here. But there has been some research in the past, especially this very seminal NeurIPS paper from Vincent Sitzman at MIT, that it's a very simple paper, very elegant and very nice, that basically just replaces the ReLU activation with the sign activation. And what this paper shows is that if you have data with like some strong natural hierarchies that kind of requires some kind of spatial smoothing or so, sign activation functions can be really useful. And obviously the processes we want to model on a sphere are going to be some where we assume some sort of spatial autocorrelation. And so we believe that these sign activations might be super useful. So we just plug it on top of our spherical harmonics position encoding and test this out. And we test this out on both synthetic and real world data sets. So the synthetic data sets are here on the left, just kind of a Fibonacci checkerboard on a sphere where the task is to classify a given location into each of these grid cells. And then the other synthetic task is basically we classify any point, again, regular points on the sphere, we classify it in, is it landmass or is it not landmass? Basically learn kind of the extent of all landmass across the planet. And the real world tasks we have are, for one, multi-task regression of ERA5. So given a lat long, we predict all channels of ERA5, which is, I think, 8 channels. It's temperature, precipitation, different atmospheric pressures, and predict all of these at once, just from a given location. And we do this time agnostic, right? We just take one ERA5 times 7. And then we also do iNaturalist image classification. And throughout the experiments, we show that our kind of new model, which is the spherical harmonics plus SirenNet, is much superior to existing methods. And this kind of performance improvement especially shows around the poles. And the poles is where existing sine cosine methods that, again, even if you do really high resolution sine cosine, you're still gonna project into an assumed rectangular domain. They fall off around the poles where the distortion between sphere and rectangular space is just much higher. Whereas our spherical harmonics functions stay pretty decently stable around there. And also our study is kind of the first one to do an actual cross-product analysis. So you see here in this figure, on the one axis, we have the different positional encodings. These go from direct, so just take raw lat long basically, to kind of the more sophisticated ones like our spherical harmonics. And then on the other axis, we have the different neural networks architectures, right? So just the linear, one layer, then fully connected, and then SirenNet. And the last thing maybe on the computation, our spherical harmonics method, because we can do.
Sorry,
yes,
again,
of course.
the previous slide. So which task are you looking at over here? Where you do the one is the Fibonacci lattice and the other one.
This one here on the right side, the globes.
Yeah.
Yes. So this on the right side is this is the. I don't have the true data here, unfortunately, but this is a single class of the iNaturalist data set. Okay. And the class is Arctic Fox. So you can see that the kind of non-spherical harmonics method returns much more Arctic Fox presence in Africa, where obviously there's no Arctic Fox. Right. And whereas our method is much more stable around areas where it actually spreads.
Okay, and I see, and so sphere is not spherical harmonic, it's something else.
Yeah, sphere M is a method called sphere to back that has been developed by Gengchen Mai. So he's at the University of Georgia now. And before that, he did a postdoc with Stefano Hermann in Stanford. And he's kind of the person who's worked most on this before us. He also came up with space to back, which was at IKEA 2020 or 21, I think, which is kind of the other big method we compare to. All of his methods were double Fourier sphere based.
Okay.
Right? So
Okay.
yeah, and I think in the interest of time, basically what this slide just shows is that our method is actually faster than the double Fourier sphere based methods until a certain number of degrees. So the Legendre polynomials you see down here, those correspond to the number of degrees, basically the resolution of our spherical harmonics embedding. And the higher you go, obviously, the more tricky for our method. But with some innovations, I think especially there's a paper that I'm very excited about. So NVIDIA actually implemented really fast torch spherical harmonics recently. So we want to kind of see if we can integrate that with our code. And then you should get up to way past 100 Legendre polynomials very easily, which is really cool.
What does that translate to in actual resolution?
Yeah, that's the other thing. I knew that and then I forgot it. So we do in our experiments, especially in the next paper, we do 10 and 40, and 40 I calculated that corresponds to changes like change is significant every 20 to 50 kilometers basically, whereas for 10 it's more like, oh, it's over 100. But yeah, this is a good question. I should write this down for the talk because this came up a few times and I always kind of try to remember. But yeah, I have some figures later, but you can see it a little bit. Right. Okay. So now we have some research on what kind of location encoders to use. Now I want to look into actually pre-training the location encoders and how to go about this and what kind of data to use. And this is the second paper I'm going to talk about. It's called SetClips. It's currently under review. And I quickly want to go back to this kind of intuition for just pre-training of these location encoders and walk you through it so things are clear again. So the intuition is the same as in my multi-model setting before, except now we really just use imagery, right? So we use Sentinel 2 images, we get a data set of 100,000 images. I'll talk about it in a second. We feed a batch of images to the image encoder, we feed a batch of the corresponding locations to the location encoder, and then the learning objective is to match location with corresponding image embedding, right? So those are both projected into the same embedding space. Now, if we do this correctly, we get a nice location encoder that, again, takes in locations anywhere on the planet and returns these meaningful embeddings. And then we can just use this location encoder downstream. For any task that takes in latitude, longitude, we can use this location encoder. It's pre-trained, it's frozen, very, very easy to use. It's only a few megabytes long. All right, let me walk you through the pre-training because that is actually quite interesting and we have some really interesting results there. And oh yeah, maybe the key innovations in this process. For location encoder, we use the Siren spherical harmonics encoder that we just talked about. And then for the data, like I said, we use global coverage, sentiment to data.
Sorry, I just don't understand this. So on the left-hand side figure, so your left-hand side figure, that location encoder is just your kind of analytics spherical harmonics location encoder.
There's no learnable parameters in there, right? In the location encoder.
There's learnable parameters. Yeah, the Siren network is a neural network that is modifiable and that will have learnable parameters. The spherical harmonics don't have learnable parameters, just hyperparameters. But again, let me go back. This is the form the location encoder takes, right? So you have the positional encoding that is purely functional, no parameters.
That's the spherical harmonics.
That's the spherical harmonics.
Got it.
The neural network on top of that is the Siren network.
Okay, I see. That's the side. Okay, so you're translating. Why do you need that additional step?
why we need that, because we want it to be learnable, right? We want to learn location encodings that are meaningful for a given task, or in this case, we do pre-training. So we
So does that mean that you're essentially clustering all the locations which have similar outputs to have similar encodings? Because you think this is a compressive sensing really at some level. It's compressive learning of the position encoding.
yeah, let me I think I'll go actually into exactly what we learn in the
Okay, great.
in the setting here. But basically, we project the locations from the input dimensions just 2 lat long into, in our case, 265 dimensions. And then we do the same with the image, and then we try to align the embedding spaces. And then that way, features are transferred into the location encoder. But I will outline exactly how that works now.
Okay.
And the intuition for that. Okay, the intuition is the following. Satellite images contain data that basically is ground conditions that make an image look specifically given the location that it is at. And these ground conditions can be something like, is there like human built structures there, right? Is there a city there? Are there mountains, which indicates that this location is in a kind of mountainous area? What is the biodiversity like? Is there a lot of plants, for example? All of these things are captured by images, and so the image features we extract should represent that. And when we match kind of images with locations, these features are being transferred into the location encoder. And if we then take forward the location encoder downstream into any other task, these we can use these features. And I think a bit more visual is a bit more visual help is this slide here. So you can see 9 different satellite images here that all capture different ground conditions. And so if we had only like this batch size of 9, we had the 9 corresponding locations, and we would try to match which image corresponds to which location. And if you see like this image right here in the middle, which I think is London, then this image can only correspond to a few locations on the planet, right? Just if you ignore the kind of uniquely London characteristics like the parks, such a dense populated area on this size can only correspond to a few locations on the planet. The same goes for this desert here, right? There's desert on different continents, but still they can only be, these can only correspond to a few areas.
So what we're learning is when we encode the image, it should be quite close to the location once encoded.
Yes, exactly. And I have a cool figure that shows exactly that.
I'm sorry, I'm this lost here. On the figure, you have P sub 1, P sub 2 up to P sub 9. But in your math, you have P with X sub I. Where did the subscript disappear for P? I'm missing something completely here.
Oh, I mean, this is just because these are just 9 examples, right? So this is kind of the full data distribution.
Isn't that X1, X2, X3? Or am I reading the notation wrong?
Yeah, I think I got the notation. I see what you mean now. Yeah, I think I just got the notation.
Okay, what you really meant is P of X1, P of X2.
X2, yeah, exactly, because it's the same distribution. Yeah.
Okay, thank you. Yeah, because
Yeah.
for me, I'm thinking of 9 probability distribution.
No, you're right. It's not. It's one distribution because we have the
Right.
whole planet.
Yeah,
covered.
that's what it is. Okay, thank you.
Yeah. But that's a good catch. I should fix
Wait,
it.
just a quick follow-on question.
Of course.
Would the model have any indication of what the scale of these images is? Or like, say if you were to zoom in a lot or use a drone instead of satellite, would it be able to?
Not right now, and this is one thing that we want to explore a lot. But right now it's all the same resolution. It's just Sentinel-2. It's the same crop size for everything. But ideally, you would want this to work with different kind of zoom levels and probably even stack different zoom levels.
Yeah, it'd be interesting to see how transferable it is, but thank you.
Yes, and what the location encoder learns, again, through this iterative process is an implicit location representation. And this is visualized here a little bit, but I'll skip this for now and go into the visualization in a second. Now, let's look at the pre-training data. So location encoders actually have been pre-trained before. There's a few examples of papers that do that. But so far, all of the data sets that have been used have been very geographically biased. For example, iNaturalist has been used, and iNaturalist, so blue dots are locations of iNaturalist images, are very heavily clustered in the US and in Western Europe. And so you see parts of Saharan Africa and Siberia or like Central Asia completely empty. And so obviously, if we pre-train using our procedure, we will just not get any meaningful information for those locations. The data set we construct is called S2 100K. It's 100K randomly sampled Sentinel-2 scenes that are approximately uniformly distributed over landmass. I said approximately uniform because we have some issues with cloud cover in certain parts of the world, which you can, for example, it's very, very small, but you can see a little bit here in the Amazon where there's a lot of cloud coverage and just makes it a bit tricky. But overall, it's still much better than any of the existing methods. And now we get to the, I think, the most intuitive figure of what our model actually learns. So the clip loss that we use, again, it tries to maximize the similarity between an image embedding and its corresponding location embedding as measured by cosine similarity. And to show what this means, I have two different anchor locations down here. So on the left side, there is a location in North America, and on the right side, there's a location in the Congo Basin. Both are marked with a star. Now we get, in this case, I think it's 100,000 other locations around the world, and see how similar is that location in the embedding space to the anchor location. And what you can see clearly here is that there's a high similarity score between the North America location and obviously other locations in North America, but also locations in Western Europe, like the UK, and in East Asia. For the Congo Basin location, we find a high similarity score between the tropical locations, right? So you find a high similarity score with parts of South America and with parts of Indonesia and Malaysia. And I think that is really the key slide that kind of highlights what this contrastive location image matching procedure actually produces.
So if you were to take the cosine similarity as sort of it's a distance metric and you do a clustering,
Yeah.
would you then automatically detect environmental biomes?
Would I detect?
Biomes, you would get the tropical
Yes.
rainforest.
I think you take one of my next slides. Yes, perfect. Yeah, so let's look into the embeddings that we learned. So here, this is just the first three principal components of different embeddings, location embeddings, taken as RGB channels and then plotted on a sphere. Up here, you can see our set-clip model, and all the other models are kind of existing location encodings. Set-clip is quite small. It's only size 265 characters, so quite small. We have two models called CSP. These are also trained using clip objective. One is trained with the functional map of the world data set, and one is trained with the iNaturalist data set. You can see that these are much more smooth. Next up, we have a GPS2Vec, which is a model trained on Flickr images and corresponding text to the Flickr image. These models are trained separately for each UTM zone of the planet. And wherever you see turquoise here, there's no model available, and so there's no location embedding available. And the last one we have down here is mosaics. This is the paper from both Esther Rolf that I cited before. This is not a trained location embedding, but basically a database. So for a given lat-long input, mosaics queries the nearest available satellite image and just returns random features from a convolutional extractor. No training involved at all. But you can see it still kind of extracts.
Can you explain that again? How does that work?
Mosaics?
Yes.
Yes. So mosaics, you put in your lat-long.
Okay.
It queries from a database the nearest available satellite image to that location, and then it does a single convolutional feature extractor, not trained at all, just random features from a convolution environment. Well, later. Does that make sense?
Not quite sure how you get the 256 dimension embedding from that.
Oh, this is the 256 dimension is just us.
Okay, right.
Okay, I can maybe say that quickly. So we are 256, CSP are both 512, I think. GPS2Vec is, both are longer than 1,000 characters, and mosaics is 4,000 characters.
Okay.
Interestingly, our method is still the most useful. And now we get to the clustering of embeddings. And so here we do a t-SNE visualization of embeddings, like it's not exactly clustering, but basically what we find is that the clusters of these kind of embeddings somewhat correspond to different hot, cold, and dry wet scales. Somewhat.
Sorry, what is TSNE?
That's a dimensionality reduction technique. It's similar, I think, just if you think about it, similarly to clustering of embedding space. I think that's a
So one question about your data set.
the pre-training data sets.
Yes, the Sentinel-2
Yeah.
images. Are they all taken from roughly the same time period?
They're taken over 2 years, and actually that's a great question because now I can talk about seasonalities. So let's say we capture the Rocky Mountain Range is a big range, we probably have at least 100 images capturing that. The images are extracted also randomly over time. So there's like an equal chance that an image that is over the Rocky Mountain range comes from July or from December. So while we don't actively incorporate time in our location reporting, we implicitly average over time because these images are taken in the sequence. So seasonalities are included in our embeddings, though our location encoders don't take in time as an. So this is kind of my last slide on the exploring the embeddings, just like so, and now I'm going to go a little bit into actually making the use of them in downstream tasks.
Can I ask you?
Yeah, of course.
What biome map was that? And you got all the, you remember who produced that? There's many different biome maps. So there's different classifications.
Yeah, what do you mean exactly?
Well, lots of different people classify the world's vegetation.
Yeah.
And there's.
Oh, which of them?
Yeah, which one did you remember?
I don't know. I can look it up and get it to you
Interesting.
after the talk. Yeah, we also use biome classification as a downstream task. And so I should be able to find which exact biome map we use, but I don't know off the top. Yeah, so yeah, of course.
So did you just use Sentinel-2? Did you try Sentinel-1 because cloud?
Yeah, we did not try Sentinel-1 yet. We might in the future, but I think more interesting than just using Sentinel-1 is using both together. And I talked about the Clay Foundation model very briefly earlier on. The Clay Foundation model is a masked autoencoder of 3 modality stack. It's a stack of Sentinel-2, Sentinel-1, and a DEM. All stacked together. So it's, I think, but they only use 10 Sentinel-2 channels, I think. They use 2 Sentinel-1 channels and 1 DEM channel. So it's 13 channel input. So something like that would be really cool.
How big is the network here?
Our neural
Yes.
So there's 2, right? There's a location and then, I don't know why I went back. There's 2. There's a location and an image encoder. The image encoder is pretty big. It's a ResNet50 or VIT16. The location encoder is quite small. It's 2 or 3 neural network layers, and so only a few megabytes. But the vision encoder is frozen except the very last layer. So we take a pre-trained vision encoder that already knows satellite data. There's pre-trained VITs for Sentinel-2, and keep it frozen except the last layer for projection. So training is actually quite fast, single GPU, and if you just use the location encoder, it's tiny. It's only a few megabytes. Yeah, so 2 kind of experiments I want to show. First, I want to kind of show that tactile embeddings actually are pretty good for general purpose use. So we do 9 different experiments in our paper. We predict, the population density, we predict country code. Input is always just that long. We predict biomes, ecoregions, and then we do also one more sophisticated experiment, which is we predict iNaturalist classes, where we combine our location embedding with an image.
So what do you mean the country code, not your telephone code? What do you mean?
No, basically we predict the country that a location is in.
Oh, okay.
Yeah. Sorry, I can just say country, And the more interesting, so this experiment really shows that we can use these embeddings for anything that we might want to use satellite imagery for, right? So it does capture broadly the change in over space that we would capture with satellite images. The more interesting thing is geographic distribution shift. and how we can use our embeddings for that. So geographic distribution shift is a problem when you're transferring a model from, let's say, continent A to continent B. But because the distribution of, for example, your outcome variable changes, all of a sudden your model fits. And this is something that we observe a lot in the real world. I think a very intuitive use case that actually happens a lot in the real world is building segmentation models were trained on US data and you transfer them to Africa. All of a sudden the houses are much closer together, they might be round shaped and your segmentation models fail. The example here is much more of a toy example. So here we train a model again from lat long to predict ecoregions. Ecoregions is kind of a smaller scale, high resolution biomes. Ecoregions can be unique to a continent. So in this example, we train on all of the world, that is except Africa, and then we add a tiny number of points, only a few hundred from Africa. So it at least has seen some of these ecoregions that are unique to Africa. And then we do prediction. Yeah.
So is this, this is training the extra layers on top of your vision encoder and your location?
No, this is a frozen location encoder. Your input is lat long. You feed your lat longs through your location encoder. You return the 265 character embedding, and then you use that to predict location.
All right.
That's the idea. You don't fine tune the location encoder. You train a new neural network.
Okay.
To keep it fair to kind of all of these other methods. And yeah, so if you kind of take existing methods, they pretty much all fail miserably at this. I think mosaics is at least somewhat useful for this task, but our cyclop embeddings are by far the most useful for this. And we've tested at this point a few other settings, including the building segmentation setting that I was talking about, and our models actually can help with that too. And that is because, again, we have pre-training unlabeled satellite imagery for the whole planet. So we can actually capture this geographic distribution shift as long as it's represented in satellite images. And our embeddings do encode that. So if you combine them with kind of models that are more prone to failing when geographic distribution shift is present, our embeddings can actually help you to prevent that to some degree. And that is just such a cool finding, I think. And again, keep in mind, this only comes from 100,000 Sentinel images. It's tiny. This model is pretty much just a prototype. And to close, I really want to hone in on some of the challenges in scaling this up and building better location encoders. And yeah, we see cyclop as not something that would be super useful in the real world, but more of a prototype to kind of show that it can be done. So the first thing is data sets. And luckily, we're seeing more and more kind of remote sensing data sets making it into the ML community, but I think there's a lot more work to be done. I think especially aligning different modalities geographically is super interesting. I think Settlers is probably a cool example of a data set that does that. And but yeah, more work I think needs to be done. The next thing is to actually develop neural network models that can deal with the different modalities of geospatial data, right? That can take in, for example, both natural and multispectral imagery, and then maybe combine it with a complete different modality, like a text that is geotagged or a video. We have like one paper on this that is under submission, basically Perceiver IO, but specifically for geospatial data. The single biggest challenge, I think, is scale, because we're looking at somewhat unprecedented sizes of data here. And the example I always give is, so GPT-3 was trained on 45 terabytes worth of tokens. And even if we assume that GPT-4 is much bigger, a single Sentinel satellite produces 1.6 terabytes per orbit, and it has 14.3 orbits a day. That's a single satellite, right? If you add stuff like climate models, which are in the petabyte domain, it's basically unfeasible to train the kind of current transformers we have with that raw data. So we need to think a lot about compression and basically dimensionality reduction before we even think about training. Learning objectives is, I think, the most fun challenge because we can play around a lot. There is a lot of work on kind of leveraging spatial dependencies for designing training objectives. So I have two papers here, one of mine from AAAI 2022, basically leverages spatial temporal autocorrelation. So there's measures of spatial temporal autocorrelation, and if you kind of predict those along with your main objective, that is already kind of an intuition for the model to help it learn spatial and spatial temporal patterns more. The other example here is kind of a vision example from ICCB, and that is one that leverages the difference in the satellite image appearance at different times of the year. So let's say you have a stack of the same location satellite image, but for all 4 different seasons, you can leverage that and kind of match correct images that are at the same location but at different seasons as a learning objective. It's called seasonal contrast, quite a successful pre-training approach. And there's so many more. Yeah, evaluation is super important, and this is a slide I think I always especially want to emphasize the computer vision community here, because we see way too much random train test splits in computer vision for remote sensing. And sure, if you only care about test sets that are kind of close to your training set, it's fine. If you just care about interpolation, it's fine. But as soon as you really care about extrapolating and having models that work outside of your area of interest, area of training, this really becomes a problem. And so we need much better evaluation schemes. We need ways for evaluating uncertainty the further we move away from the train set. And yeah, the checkerboard I have here is just a cool approach that I think a few papers have used that now, but again, Esther's paper, the mosaics paper, that is, does that really well. And you kind of split your world into kind of checkerboards that are bigger or smaller, depending on how you define it, and that kind of can give you a really interesting train test split.
Quick question. Is
Yeah,
that how you did your evaluation is by from using the checkerboard splits or the checkerboard training test split for your experiments?
In our paper? No, we did not use the checkerboard split. We did the holdout continent split, where we train on the whole world and leave one continent on. We decided against this, but maybe in the future we might use it. And yeah, so the last thing I wanna close with is the slide that I had promised. I think that while geographic location encoders are kind of a more abstract thing that it's not necessarily super accessible to people, I think we can actually make it more accessible by this cool fusion we see nowadays of LLMs and all sorts of other foundation models. And this came up in the lab talk, but you can combine natural language models with segmentation models, for example, and you can develop software that basically allows non-experts to interact with these models. And this is from the segment Geo website, SamGeo website. Basically, this example of you have an image and you can text prompt the model to find stuff in this image, in this case, a tree. So you can type in tree and then voila, segment anything model will find all the trees for you. So yeah, I really hope that we can kind of make location encoders useful for everyone, and I think this is a cool way to do this. Yeah, so I've talked about 2 papers here. One is going to be spotlighted at ICLR in Vienna in May. So if you're around, can meet up. The other one is currently under submission, and I have amazing authors, especially Mark, who's at Wageningen, and Esther, who's at Harvard, but also great senior people like Caleb at Microsoft, Lester at Microsoft, and Davis at EPFL. And I'm exactly at time. But I'm around, so if you have any more questions, I'd love to hear them. And thanks for coming.
Thank you. I think we've asked Konstantin lots of questions.
Yes, yes.
Already, but are there any other questions?
Yeah, thanks.
Thanks for the talk. I'm wondering, like, if my understanding is correct, this model is like a continuous function over the locations where you input any longitude or latitude, you can output representation vector.
Yeah.
It can be used as an interpolation model. So how is this compared to some other methods like the Gaussian process or neural process? These models are also used to interpolate the precipitation and other data.
Yeah, so this question is more relevant to the first paper where we actually do direct location to outcome prediction and no pre-training step. And we were thinking a lot of time if we should include GP baselines here. And we decided against it because I think it would have made things even more confusing. The purpose of the spherical harmonics location encoding paper was really to compare one neural network method with other neural network methods. But I still want to do this. I think I want to do big comparison studies that compares GPs to neural network location encoders. And you're right, they're trying to do exactly the same thing. I think my intuition is that probably, so I originally come from GP, so I think that they're maybe the strongest model, we just can scale them and so we don't use them, but my intuition is they're probably better until a certain size, and then they might still be better, but they're just unfeasible. And especially I would like to compare these kind of location encoders to the more like the more modern GPs that are meant for high dimensional data, like deep GPs and so on. But yeah, we haven't done the comparison yet.
Just a quick question.
Yeah.
Amazing work. Especially about, because I do a little bit of work on explainability, and I really like the different little trying to explain these different dimensions, perhaps the same thing, or the PCA of the TIS. It's really good. In terms of interpreting, do you have any insights on how what other things you can do in this? For example, have you thought about, like, I don't know, rather than an image encoder, a text encoder, and see where actually, like, what it is reading, or if there's any, like, do you have any intuitions from an interpretability perspective? And second question is related to, you know, this paper of GraphCast from DeepMind? Because that kind of use a more GNN approach. Did you, like, what are your thoughts on combining it or comparing it?
Okay, I'll answer that first. So I think GNNs is, I think it goes also towards the GP question. So doing a big comparison between neural network location encoders, GNNs, and GPs would be really cool and really useful for the public. But we have not done that yet. The only thing I can say is that we have a paper that combines them, or like I have a paper that combines them. Yeah. So, and that I think is interesting in a sense, because we take two methods that should do the same thing. Location encoder projects input to output, and the GNN also input to output. And both are meant for spatial data. And we show that if you combine them, they're actually even better than just having one of them. But yeah, again, I think there's so much work to do on just kind of not new methods necessarily, but the kind of the boring, tenuous work of doing big comparative studies between these different methods. And then the first question was on interpretability of the embeddings.
Or or do you have any intuitions or
except the ones that we made with kind of clustering them along biomes. Not really. I wanted to, let's stop sharing my screen for a second, because there was also the question about the resolution of the embedding. So I kind of want to show, oh, you can still see my screen. Yeah, you can keep asking questions, or quickly try and
Why don't we
find.
do this? Let's stop the recording here.
Yeah.
And then you can share your screen.
Actually, that's good.